Good day, ladies and gentlemen. We are all welcome to lecture number 6 of Cmen405 Digital Electronics 2. In this lecture, we are going to see an introductory aspect of algorithmic state machine, ASM. And to begin with, we need to know that the binary information that we process using digital circuits, they are of two types. The first one, we have a data that we manipulate in order to give us output from the input, and of course we have the second segment of the binary data, which is the control information, which is like the signal responsible for changing the behaviors of our input until we get the output. And as I said, this command information, its function is to command and manipulate the data so that you can get the result from your inputs. And in digital systems, when we are designing with respect to this fact, we have two segments. We have a circuit that is used for processing the raw data, and we have a circuit that is for controlling the behavior of the digital system. And this segment that is responsible for that control is what we call algorithmic state machine. And as we can see on this block diagram, we have two rectangles. The first one is the control logic, and the second one is the data processor. Our function or our requirement is to apply input into this our data processing or processor to get the required output, but that is not possible without the control signal from this control logic. So for this, there is need of design and analysis of that control segment, and that is what the algorithmic state machine is all about. And since I told you this one is an introductory aspect of this ASM, we will be limiting ourselves to statements that will be transformed into a flow diagram, or a flow diagram that can be translated into the statement describing the behavior of the algorithmic state machine. And this diagram is what we call Asm chart, and for us to draw it, we have three basic elements. The first one, we call it a state box, the second one is decision box, and the last one is conditional box. And this rectangle you're seeing here is what we call the state box. It is rectangular in shape, and as you can see from the diagram here, it has one entry point and it has one exit point. On the left hand side of the box, we write the name given to it, and on the left hand side we write the binary code equivalent to that name, and inside it register operation takes place, and also we can deliver an output of such data. A typical example is given here, where we said the name of this our state box is T2 and the binary code is 101. It can be any binary code. And what is taking place inside here is that we will clear this register R to 0. The moment you say you clear something in digital, you are resetting it to 0. So this arrow is saying that the value of R, whatever it was previously, we are going to clear it to 0, and then we start the process of the algorithmic state machine. The second box, as we have said, is conditional box, and it is diamond in shape, as you can see here. And the conditional box is used for decision, and for this reason it has one entry but it has two exits, because whenever you are taking a decision, there are two possibilities. Your decision can be accepted or rejected. It can be yes or no, it can be high or low. That is why we have two exits, one for 1, that is when the decision is true or the condition is true, and the other one is 0 when it is false. And inside it we write the condition we are testing. And the last of the three elements of the ASM chart is called the conditional box. This one is a decision box, the one I have finished, and the last one is conditional box, and it is oval in shape. In this oval shape conditional box, it has one entry point and it has one exit point, and inside it we write an operation that can take place, or we write an output. Now the next thing is to give a symbolic notations for register operations. We said register operations do take place in state box or in conditional box. So how do we write them in logic notation? These are some examples. For instance, here you see I have an A here, I have B here, and my arrow is moving from B to A. What it is saying is that we should go to register B. Whatever is containing it, we now transfer them to register A. And if you look at the second one, we are saying that this our register R, we should clear it to 0. That is clear register R to 0. And here we have A plus 1 pointing to A. What we are saying is that we should increment the value of the register A by 1, and whatever we get as our result, we should store it in the same register A. And here we have A minus 1 pointing to A. It means we should decrement it, reduce it by 1, and the result should also be stored in the same register A. But here we are saying that the content of register A and content of register B should be added, and the result of that addition should be stored in register A. These are some typical examples of notations we use when writing register operations. So for us to appreciate what we are saying, let us take work example number 1. And the question says, draw an ASM chart of a state machine in which the control generates a start output signal when it is in state T1 with binary code 1001. Then while it is in this state, that is state T1, the control checks the status of input E. Whenever you're checking status, you are testing a condition, you are making a decision. So we set, if this E that we are checking its status is 1, the register should go to, that is register R should be set to 1. Otherwise, that is if E is not 1, definitely it should be 0. Then it is cleared, that is we set the register R to 0. In case this E is equal to 1, the next state is T2 and it has a binary code of 1101. But when E is equal to 0, that's the otherwise condition, it will return to its initial state T1. Okay, this is a typical example, and let us see how we solve it. So to solve this problem, first of all, we look at the question. We are asked to draw a ASM chart in which the control will generate start when it is in state T1 with this binary 1001. So this is what happened. This is my first state T1, and the binary code equivalent to it is 1001, and inside it the operation is to start the machine. Now after that, it will now go and check the states of the control E. That is, we have a register E, we want to check its condition, and whenever you are checking, as I've said, you must use a decision box, and that is why I have my decision box here, and this is my E. I'm checking the condition for E. So what are we told to do? If E is equal to 1, it will clear a register R it will set it to 1. So look at what we have here. When this E is 1, we have a conditional box where our R is set to 1. And otherwise, that is, if it is not equal to 1, it should be 0, then it will clear the register R. That is, when E is found to be 0, we clear this register R to 0. So then what? In case this E is equal to 1, after setting the register R, then it will now go to state T2, and this is its binary code. But if it is 0, it will clear the register as we have seen, and it will go back to T1, and this is what actually happened. That is, when E is equal to 1, we are told that register R should be set to 1, and then it should go to state T2 with this binary code. In a situation where E is equal to 0, it will clear this register and go back. As simple as this. This is how we draw this ASM chart for this question. And additionally, after drawing ASM chart sometimes we are asked to draw state diagram. And if we can remember how we did this one under sequential logic analysis, we'll remember that what we are concerned with here are the states. And if you look at this, I have two states. I have state T1 and I have state T2, and I'll write two cycles for T1 and T2. I don't write the T1 and T2, but I'll write their binary codes. This is 100 and this is 110. Now, what is the condition for moving from state 1 to state 2? We can see that the condition is that our E must be equal to 1. So we write E equal to 1, it will move to this. But what is the condition for this T to come back to itself? Our E must be equal to 0, and you can see when E is 0, we go back to that. Therefore, all these conditions, they are eliminated. The decision is just indicated by using this lattice, but we don't use the decision boxes. So this is question example number 1 on ASM. Now for us to further understand it, let us take example number 2. The example says draw an ASM chart of a state machine in which the control increments A by 1 when it is in state T1 with the binary code 101. So let us see that. We are told that we are starting from state T1, and this is the binary code, and the operation that will happen inside that state box is to increment our register A by 1. Look at it, A plus 1, and of course the result should be stored in the same A register. So after that, what will happen? While in state T1 with a binary code this, while in this state, it will check the input state of E condition. If E is equal to 1, it clears R to 0 and moves to T2. That is, this is my condition box. When this E is equal to 1, it will clear this register R to 0. We use conditional, a box oval, and it will move to T2 with the binary code 001. Then what? But if E is cleared, that is, it is equal to 0, it will now check the input of another register, that is another condition testing, F. Look at it. When this E is equal to 0, it will go to another decision box where we are going to test the condition of F. Now, if F is equal to 1, the register R is set to 1 and it moves to state T3 with binary code 110. That is, when this E is found to be 1, it will go to a conditional box oval to set our register R to 1 and then move to T3 with binary code 110. Then, what if F is equal to 0? Look at it. But if F is equal to 0, it will move to another state T4 with binary code 010, and look at it here. If this F is happen to be 0, it will go to T4 with 010 as its binary code. Now, finally, when in state T4, it checks the state of the input G, another condition box. If G is equal to 1, it will set register R to 1 and go back to T1. That is, after this state T4, we test the condition for G. If G is equal to 1, R is set to 1 and it goes back to the initial states. What of if G is equal to 0? It will go back to T2. That is, when G is equal to 0, it will directly go back to T2. Now, fantastic and very simple. This is how to draw this ASM chart for the example number 2. And as we did, if you look at it here, I have states T1, T2, T3, and T4, 4 states. So I can be asked to draw the state diagram. How do I do it? I'll put my 4 states here, 010 for T1, 001 for T2, 110 for T3, 011 for T4. Then what's the condition of movement? Look at it. If I want to move from T1 to T2, my E must be equal to 1. And look at what I did. When E is equal to 1, I move to T2. And going back here, If I want to move from T1 to T3, my E must be 0 and my F must be equal to 1, two conditions. So look at it, my EF 0, 1 to move to T3. And then if I want to move from T1 to T4, what are the conditions? My E must be 0 and my F must also be 0. Look at it, if I want to move from T1 to T4, my E and F are all 0, 0. Now, from this T4, if I want to go back to T2, the condition is for G to be 0. And look at it, when G is 0, we move from here to here. But if I want to move from T4 back to T1, my G must be equal to 1. And look at it, my G is 1. We go back to this. So therefore, ladies and gentlemen, this is the end of this lecture number 6. And as I usually advise, I urge you to sit down carefully, watch the tutorial over and over, and try to comprehend. In case you still have problem, you can contact me for clarification. Thank you. Till we meet in the next lecture, lecture number 7.